As we said before, even if the null hypothesis is true, the test statistic can be different from zero by chance. So under the null hypothesis, there would be no effect, so the test statistic should be theoretically equal to zero, but due to randomness in the data, it can be different from zero. The way to check how likely such a deviation from zero is through the distribution. So we will look at the distribution of the test statistic, assuming that the null hypothesis is true. So we take a distribution under the null hypothesis, and then we get an idea about which deviations are likely. So how much can we deviate from zero and still accept the null hypothesis? And from what moment on do we reject the null hypothesis and would we select the alternative hypothesis? If we then take a look at the distribution, we know that the largest probability is in the center, and in the center is also zero. So zero is the center for a standard normal distribution or for a t-distribution. And so if there is no effect, we expect to have a value of zero. So around zero will be the region in which we will not reject the null hypothesis. We call this the acceptance region. So here we do not reject the null hypothesis. Once we are too far away from zero, then we will reject the null hypothesis, and we call that part the rejection region. The alternative hypothesis was that on average, the systolic blood pressure changes after administration of captopril. We call this a two-sided alternative because the direction is not important. So we are not looking at an increase or a decrease, we are just looking at an effect. Is it different, yes or no? Then we will reject the null hypothesis if my test statistic is in either one of the tails. So either it is smaller than a value minus c or larger than a value c for some positive c. If we allow for 5% risk for type 1 errors, this means that we have 5% of rejection region, what we called in the previous slide, and it's split equally because we have c and minus c, so the distance is the same to the center, which also means that the tail on the left and the tail on the right side is the same, they have the same surface. So if we allow for 5% of errors, this means that we allow for 2.5% on the left and 2.5% on the right. So in a two-sided alternative, we always have the center and the left and the right sides which are equal. So if we have a 5% significance level, this means we have 2.5% on the left and 2.5% on the right to exclude, so to have a rejection region. If we go back to the captopril example, we have the systolic blood pressure. We know that the test statistic follows a t-distribution with n-1 degrees of freedom. Then if we plot this, we see that the blue line, which corresponds to the value of the test statistic, so -8, is far in the left side tail. The red dotted lines correspond with our threshold, so 95% of the data is in the center, 2.5% to the left, 2.5% of the right. So we are testing here at the 5% significance level. And we see that in this case we will reject the null hypothesis because clearly we have no evidence that the null hypothesis is true. The test statistic value is in the tail, it is far away from the center, it falls outside of the thresholds. How will we determine these thresholds? Basically, we will use the quantiles. We know that 95% is in the center, 5% is spread over both tails, so 2.5 on the left, 2.5 on the right. So what we need is the 97.5 percentile for the value. So C will be the 97.5 percentile for a t-distribution with n-1 degrees of freedom. In our case, this is 2.14. And now we compare -8.12, which is our test statistic, with -2.14 because we're on the left tail. And we see that it is smaller, so it is outside our acceptance region. Therefore, we can conclude that the mean systolic blood pressure in the population will change after we give the patients the drug captopril. Please remark that it's also important to formulate an answer to the research question. So it's not just sufficient to say we reject, we accept, but add a wording, a descriptive sentence which explains your result, which explains what your answer to the research question is. Don't just say I reject or I do not reject, but write it, describe it in words. The test that we have just performed is a one-sample t-test. A one-sample t-test will test the mean of your characteristic, of your variable, against a fixed value which you assume to be true. So you have your null hypothesis, my population mean is equal to some value mu0, and my alternative is mu is not equal to mu0 for a given mu0. So we have a test, a one sample test because we have only one sample and we compare the sample data with a fixed value mu0, and a t-test. Why a t-test? Because we do not know the population variance, so we have to estimate it. So a one sample t-test is used to check if the mean of a continuous measurement will deviate from a certain value of mu0. So your test is basically testing mu equal to mu0 or mu different from mu0 in a two-sided one sample t-test. The test statistic we saw before is my sample mean minus the value I am comparing with, so the value I assume for the population parameter. In the captopril example it was 0 because we assumed that there was no effect, so an effect of 0, and then we divide by the standard error. Then under the null hypothesis, so we assume that the null hypothesis is true, we know that this test statistic will follow a t-distribution with n-1 degrees of freedom. Now, what are the conditions for a one sample t-test? The condition is that the data are independent, so we have independent observations, which is again difficult to check. We will assume that this is correct through our sample design. And we want that the data are normally distributed or that the sample is large enough such that the sample mean is approximately normally distributed. So this is a condition that we will have to check. We will have to see if my x bar follows a normal distribution or not. In our test statistic, we estimated the standard deviation with the sample standard deviation. So we assumed that sigma is not known. However, if sigma is known, we can use the exact value for this. In that case, a couple of things will change. So my test statistic will not be x bar minus mu0 over s over square root of n. It will become x bar minus mu0 divided by sigma over square root of n. Then, of course, under the null hypothesis, this will not follow a t-distribution, but it will follow a standard normal distribution. So our test statistic will not be indicated by the letter t, it will be indicated by the letter z, and we will call it a one sample z test instead of a one sample t test. Of course, sometimes we are interested in seeing if the effect is positive or negative and not just different. So in that case, we will not have a two-sided t-test, but a one-sided t-test. We are not interested in a difference in both directions, but we are interested in a specific direction. And then you have left one side or right one side. What changes? Well, of course, the hypothesis will change. So the null hypothesis will not change. We will keep the null hypothesis as mu equal to mu0, but the alternative hypothesis will not be different from, but will, depending on the case, be mu smaller than mu0 or mu larger than mu0. The test statistic itself will not change, so this one remains the same, but we will compare it to a different threshold. So in the case of a one-sided test, our threshold is on the left side or on the right side, but not on both sides. For the threshold, we know that we have to have a rejection region which contains 5% of the data, so 5% of the area under the curve. And so the quantile that we need is not the 97.5 percentile, but the 95 percentile, either a positive or a negative value, depending on the case if we are testing on the left side or on the right side. But we will look at the t-distribution, and for the t-distribution we will take the 95 percentile instead of the 97.5 percentile. And then the conclusion is the same. You determine the acceptance region, you determine the rejection region, and you then compare your test statistic value to the threshold that you have calculated, that you have found in your tables. So if it is more extreme than the quantile that you found, then you will reject the null hypothesis. More extreme means for a left-sided test more negative, and more extreme for a right-sided test is more positive, so more to the right side. So then you are in the rejection region, you reject the null hypothesis and you will go for the alternative hypothesis. So up until now you have two options to determine rejection or not. Either you first determine the rejection region and the acceptance region, and then you check is my value, the value of my test statistic, within the rejection region or the acceptance region, or you just determine the quantile that you need and you compare the quantile to the test statistic. Basically, both of these methods are the same because determining the rejection region will need to have information on the quantile, and so you cannot determine the rejection region without the quantile, but the mindset is a little bit different. So you look at a region and you see if my value is in the region, yes or no, or you look at the threshold and you see is my value farther away from the center than the threshold, yes or no.